Hello everyone. In this video, this is I think the 8th video in our series. In this video we're going to continue with application of the derivative, application 2, involving word problems. Before we do that, I want to talk to you a little bit about interpreting slope in terms of rate of change. And so on the board here, I have drawn two graphs. On the graph on the left is the graph of a straight line. And you know the slope of the line is the same at every point, right? And slope measures the steepness of the line. And we measure the steepness as rise over run. Well, I want to talk about slope in a different context, using a different wording, okay? Describing it differently. Okay? The slope, rise over run, right, is found by taking the difference for 2 points on the line, taking the difference in the y coordinates over the difference in the x coordinates, right? So we have change in y over change in x. Okay? And in this example, okay, for every 1 unit, the slope is 2. So for every 1 unit increase in x, there's a 2 unit increase in y. And so y increases 2 units for every 1 unit increase in x. Slope is another way about talking about how fast the variable y changes as the variable x changes. And we call that, in this case, instantaneous rate of change. Every time the variable x increases by 1 unit, the variable y increases by 2 units. That's called rate of change. Over here, I have the graph of an arbitrary function, and I've labeled a point here. And we know to find the slope of the point, or the steepness of the curve at this point, all we have to do is differentiate the function f of x and get the derivative f prime of x. And f prime of x tells us how steep the curve is at each point on the curve for each value of x. Well, the slope, or the derivative, also tells us how fast the variable y is changing at that point as x changes. And it is it's called the instantaneous rate of change because we know the slope is changing as we move along the curve. And so the derivative can be thought of as how fast the variable y is changing as the variable x is changing. And we call that instantaneous rate of change. And the derivative then has an interpretation, it's like a velocity. When you drive down Highway 501 in your car, right, your velocity, right, should be 50 miles per hour, right? 50 miles per hour is a velocity. So in thinking of the slope as rate of change, and in this case instantaneous rate of change at a point, it's like a velocity. It's like miles per hour. That's important concept as we work on these word problems in the second application, okay? So if you turn to page 27 in your packet. Now, yesterday I realized most of you have the short packet that I distributed at the beginning of the semester. And that packet did not have a cover page on it. Some of you bought the full packet in the bookstore and paid the $5.70. That packet had a cover page on it. So the numbering between the packet that most of you have and the packet that some of you bought in the bookstore differs by 1. So when I refer to page 27 in my packet, if you bought the packet at the bookstore, it's page 28 in your packet because you purchased it in the bookstore and it has a cover page on it, okay? So I apologize, I just realized that yesterday. So let's take a look at this first example. you're given a chain pizza restaurant is installing pizza warmers into their fleet cars. The number of fleet cars with pizza ovens installed is given by this function. V of t is equal to 0.7 times e, and that's a decimal. I wish there was a 0 in front of it. That's e raised to the 0.12 t power. So this is an exponential function, where v of t is measured in thousands of vehicles, and t is measured in years. And t equals 0 corresponds to the year 2012. Okay? So t, instead we don't have x now, okay? And we don't have f of x for the name of our function. The name of our function is v, and the independent variable going into the function is t for time. In math, we often use the variable t for time. So t is the year, and v of t tells us the number of cars that are installed with pizza warmers. Okay. In part A, you're asked, what was the number of vehicles with pizza warmers in 2015? Well, what's the value of t that corresponds with the year 2015? So I'm going to draw a little table over here. We know that t equals 0 corresponds with the year 2012. So if I add 1 to both sides, that means t equals 1 corresponds to the year 2013. Then t equal 2 corresponds to the year 2014. And then t equal 3 has to correspond to the year 2015. So to find the number of vehicles with pizza warmers in 2015, we plug in t equals 3 into the function up here. So when we do that, we have v of 3 is equal to 0.7 times e raised to the 0.12 times 3 power. All right, so I just replaced the t on the right-hand side with 3. You got to simplify the exponent, right? You got to follow the order of operations in calculating this number. You're going to need a scientific calculator. 0.12 times 3 is 0.36. So we have 0.7 times e to the 0.36 power. And exponentiation comes before multiplication. So this is equal to 0.7. Now I'm going to use parentheses to indicate multiplication so we don't confuse decimal places with multiplication symbols. And using your scientific calculator, e raised to the 0.36 power is 1.433329 to 6 decimal places. Okay? Now you don't have to write the number down. You just leave this number in your memory in your calculator. Okay? I'm just doing it so you know what that number's roughly equal to. And now when we multiply 0.7 times this number in parentheses, we get 1.003 to 3 decimal places. Okay? Now, why did I round to 3 decimal places? Because v of t is measured in thousands of vehicles. Not number of vehicles, thousands of vehicles. So the number of vehicles with pizza warmers in 2015 is 1.003 thousand vehicles. Because capital V, V of t, its units is thousands of vehicles. Okay? Now, that's why I went to 3 decimal places, because 1,000, right, is a 1 with 3 zeros behind it. So if I multiply this number by multiply 1.003 by 1,000, I get 1,003. And so 1.003 thousand vehicles is the same as 1,003 vehicles. You can leave your answer in either form, I don't care. In part B, it asks how fast was the number of vehicles with pizza warmers changing in the beginning of 2015. So whenever you get a question that asks you how fast was something changing, right? How fast were you going down Highway 501 when the patrolman pulled you over for speeding? Okay, right? That's a velocity. So our answer here, right, is going to be like a velocity. And to find, whenever you have an answer that's like a velocity, you need the derivative of the function. Okay? Because the derivative of the function tells you how fast something is changing. So before we can calculate how fast the number of vehicles with pizza warmers was changing in the beginning of 2015, we need the derivative of v of t. And so the derivative of v of t is v prime of t. And now we're going to use the rules of differentiation to find the derivative on the right-hand side. Well, 0.7 is a multiplicative constant. You know we just carry that along. And then we multiply that, I'm using parentheses to indicate multiplication, and then we multiply that by the derivative of e to the 0.12 t power. Well, that's the natural exponential function, and to differentiate that, we have to use the chain rule applied to the natural exponential function. The derivative e to the 0.12 t power is itself. And then we multiply that times the derivative of the exponent. Well, the derivative of 0.12t is 0.12. And now, right, when I multiply 0.17 times 0.12, I get 0.084. And then that's being multiplied by e raised to 0.12 t power. So that's the derivative of v of t. Okay, derivative v of t is 0.084 times e to the 0.12 t power. Now to find how fast the number of vehicles with pizza warmers are changing at the beginning of 2015, we just plug in t for 3. Because t equals 3 corresponds to the year 2015. So v prime of 3 is equal to 0.084 times e raised to the 0.12 times 3 power. Well, again, 0.12 times 3 in the exponent is 0.36. So 0.084 times e raised to 0.36 power. And that number, e to the 0.36, using your calculator, we know is equal to 1.433329 from up here. Right? We already did it up here. And so when we multiply this number in parentheses up here by 0.084, we get 0.120 to 3 decimal places. And again, I'm doing it 3 decimal places because v of t is in thousands of vehicles. So we have 0.120 thousand thousand what? What are the units? Well, this is like a speed. So instead of vehicles, or instead of miles per hour, like when you're driving down 501, it's 1,000 vehicles per year. Because V of t is thousands of vehicles, and t time is in years. So the speed or the velocity is 1,000 vehicles per year. And now if I multiply, okay, 0.120 times 1,000, I get 120. This is equal to 120 vehicles per year. So the number of vehicles that were getting pizza warmers at the beginning of 2015 was increasing at the rate of 120 vehicles per year. Okay? So whenever you're asked how fast is something changing, the answer is like a velocity. It's something per something. Okay? It's a rate of change. All right. In the next example, I'm going to see if I can make this a little smaller and see if we lose anything as a result. I was a little pinched for board space on that problem. In example 2, reading through it, in the wake of the 2008 financial crisis, the number of bank failures began to fall sharply between 2010 and 2020. The number of bank failures from 2010 through 2012, oh, excuse me, I said 2020. In the wake of the 2008 financial crisis, the number of bank failures began to fall sharply between 2010 and 2012. The number of bank failures from 2010 through 2012 is described by the function f of t, which is equal to 48 times e to the minus 0.83 t power, where f of t is measured in thousands of bank failures, right? So f of t is in units, or is in thousands again, and t is measured in years, like in the previous problem. And t equals 0 corresponds to the year 2010. In A, you're asked what was the number of bank failures in 2011. Well, draw my little table over here again. If t equals 0 corresponds to the year 2010, then t equals 1 corresponds to the year 2011. So to find the number of bank failures in 2011, we just plug in 1 for t up here, because f of t tells us how many bank failures there were, and thousands of bank failures, okay, for each year t. So f of 1 is equal to 48 times e to the minus 0.83 times 1 power. Again, I'm using parentheses to indicate multiplication because I don't want to confuse decimal places with multiplication symbols. And minus 0.83 times 1, you know, is minus 0.83. So this is equal to 48 times e to the minus 0.83 power. And using your calculator, right, exponentiation comes before multiplication from the order of operations. Using your scientific calculator, e raised to the minus 0.83 power is equal to 0.436049 to 6 decimal places. And now when we multiply these two numbers together, we get 20.930. 20.930 what? Right? Ask, what was the number of bank failures in 2011? Well, remember, F of t is in thousands of bank failures. So the answer is 20.930 thousand bank failures. And again, you multiply this number by 1,000, and the number of bank failures is 20,930. Okay. 20.930 thousand bank failures is the same as 20,930 bank failures. In B, it asks how fast was the number of bank failures changing in the beginning of 2011. So again, it's asking how fast was something changing. Well, that requires a derivative. And so we have to differentiate f of t in order to answer how fast was the number of bank failures changing in the beginning of 2011. So f prime of t is equal to, again, right, this 48 is a multiplicative constant, so we just carry it along. And then in differentiating e to the minus 0.83 t power, right, we have to use the chain rule. And so the derivative of e to the minus 0.83 t power is itself from the rules of differentiation. And then by the chain rule, we have to multiply that by the derivative of the exponent. And the derivative of minus 0.83 t is minus 0.83. And when I multiply 48 times minus 0.83, I get minus 39.84. So f prime of t, the derivative of f of t, in this case is equal to minus 39.84 times e to the minus 0.83 t power. Now to find how fast the number of bank failures, how fast was the number of bank failures changing in the beginning of 2011, we plug in 1 for t, okay? Because t equals 1 corresponds to year 2011. So f prime of 1 is equal to minus 39.84 times e. And when I put in 1 for t here, I have minus 0.83 times 1, which is just minus 0.83. And we know what this number is equal to, e to the minus 0.83. We calculated it up here. It's 0.436049. So when I multiply 0.436049 times minus 39.84, I get minus 17.372. Well, minus 17.372 what? 1,000 bank failures per year. Remember, it's like a velocity. 1,000 bank failures per year. Right. Velocities, like miles per hour, is something per something, okay? And so the something in this case is 1,000 bank failures, and the other something is year. So minus 17.372 thousand bank failures per year. And when we multiply this number by 1,000, we get minus 17,372 bank failures per year. So the number of bank failures, right, was decreasing at the rate of minus 17,000, was decreasing at the rate of 17,372 per year. Okay? That's a negative, means they were decreasing. The number of bank failures was decreasing at the rate of 17,372 per year. All right, so that is examples 1 and 2 in your packet under the second application of the derivative. Okay. In the next video, we'll cover example 3.